Hello everyone, this is Nasna, currently pursuing MSc Ed Physics from RIE Mysore. In this section, I will be discussing about two-dimensional nanostructure. Before going into two-dimensional nanostructure, let me briefly define what is meant by nanomaterials. So basically, nanomaterials are the materials in which at least one dimension lies in the range of 1 to 100 nanometers. There, the 100 nanometer, which is the upper limit, is the limit where the quantum and surface effect begin to dominate over the bulk behavior. At this scale, materials no longer behave like their bulk counterparts, and they will have, that is, the nanomaterials will have unique properties different from bulk materials. These differences arises mainly due to two reasons. The first one is quantum confinement. When the size of a material became comparable to the de Broglie wavelength, that is electronic de Broglie wavelength, the energy level becomes discrete. This directly alters electronic, optical and even magnetic behavior. And the second reason is higher surface to volume ratio. As the size decreases, a large fraction of atoms lie at the surface, which enhances chemical reactivity and can also modify mechanical property. Based on how many dimensions are confined at the nanoscale, they are classified as 0, 1, 2 and 3 dimensional system. That is, the same chemical compounds can exhibit extraordinary different properties when they are configured into a 0, 1, 2 and 3 dimensional crystal structure. I have given the examples for the classification of nanomaterials. You can go through that. Now, focusing specifically on two-dimensional nanostructure. In two-dimensional nanomaterial, the thickness is confined to the atomic scale, typically around 0.3 to 5 nanometers, corresponding to one or few atomic layers, while the lateral dimensions are much larger. And one defining feature is the presence of strong in-plane covalent bonding. This gives these material high mechanical strength and structural stability within the plane. At the same time, the layers are held together by weak out of plane van der Waals interaction. This anisotropy is crucial because it allows easy exfoliation into thin sheet. Because of this reduced dimensionality, electrons are confined in one direction, leading to quantum confinement effect. As a result, the 2D material exhibit unique electronic, optical, thermal and mechanical properties that are fundamentally different from their bulk forms. Now, let's look into some important examples of two-dimensional nanostructure. The first one is graphene, which is a single atomic layer of carbon atoms arranged in a honeycomb lattice. It has a zero band gap and extremely high electrical conductivity, along with the exceptional mechanical strength. Graphene is often considered the prototype of all 2D material. And the next one is transition metal dichalcogenates, that is TMDs. Unlike graphenes, these materials are the semiconductor with a tunable band gap, making them suitable for the transistors and photoelectronic devices. A key feature is the transition from an indirect band gap in a bulk to the direct band gap in a monolayer. And another important 2D material is hexagonal boron nitride. It has a structure similar to graphene but behave as a wide band gap insulator. Due to its excellent thermal stability and atomically flat surface, it is widely used as a dielectric layer and a substrate in a 2D heterostructures. We also have MSc, which are the two-dimensional transition metal carbides or nitrides. These materials are electrically conductive and hydrophilic, making them promising for energy storage and sensor application. And graphitic carbon nitride. It is a two-dimensional semiconductor primarily studied for photocatalytic applications, especially hydrogen generation and environmental remediation. Finally, nanofilm or thin films, which represent a broader class of two-dimensional structure with a thickness from 1 to 100 nanometers. Depending on the material, metallic and semiconducting or oxide, they are widely used in electronics, sensors and protective coatings. So, by looking into this, we can answer to the question why graphite cannot be used directly in the transistor. As we already know that graphene lack a band gap, so it cannot be effectively switched off. That's why we can't use graphite directly in the transistor. So as I mentioned before, the two-dimensional nanostructure shows properties that are fundamentally different from their bulk counterparts because of electron phonons and even mechanical deformation are confined within a single atomic plane. Now, when we look into the mechanical property, mechanically, these materials are exceptionally strong yet flexible. This comes from strong in-plane covalent bonding, while out-of-plane interaction are weak van der Waals force. The next one is surface property. Because almost every atoms lie at the surface to volume ratio is extremely high. This makes two-dimensional material highly reactive and very sensitive to environmental changes. When we look into electronic properties, electronically, two-dimensional material offers tunable band structure and a high carrier mobility. For example, graphene has a zero band gap, which is great for transport but poor for switching. In contrast, transition metal dichalcogenates like MOS2 have a finite band gap, making them suitable for transistor. Hexagonal boron nitrate, on the other hand, is a wide band gap insulator. The next one is optical property. Optically, these materials show strong light matter interaction. Interestingly, their absorption and emission properties depend strongly on the number of layers. And the next one is thermal property. Thermally, two-dimensional material exhibit anisotropic conductivity. Heat flows very efficiently within the plane, but purely perpendicular to it. Next one is quantum effect. At the atomic thickness, the quantum confinement became significant. This lead to novel electronic, optical and sometimes magnetic properties that are absent in bulk materials. And the next property is chemical. Chemically, their active surface allow easy functionalization, which is crucial for sensing, catalysis and energy application. And then layer dependent. Finally, many properties depend strongly on the number of layers, making thickness an important tuning parameter. So when we look into the examples of two-dimensional nanostructure, the first one is nanofilms. So it can be also called thin films. Nanofilms are ultra-thin solid films with a thickness below 100 nanometers deposited on a solid substrate. They can be fabricated using chemical vapor deposition, physical vapor deposition and atomic layer deposition. Among these, atomic layer deposition offers atomic level thickness control, which is critical for nanoscale devices. Due to quantum confinement, nanofilm shows altered electronic and optical properties and often behave as quantum wells. As a result, nanofilms are widely used in electronic, optoelectronics, sensor, coatings, and energy devices. The next example of two-dimensional nanostructure is graphene. As I already mentioned, graphene consists of a single layer of sp2 bonded carbon atoms arranged in a honeycomb lattice with a thickness of 0.34 nanometer. It can be synthesized through mechanical exfoliation, chemical vapor deposition on a metal substrate, liquid phase exfoliation, or by reducing graphene oxide. Electronically, graphene has a zero band gap and extremely high carrier mobility, which exceeding 200,000 centimeter square per volt second. However, the absence of a band gap limits its use in digital logic. Mechanically, graphene is one of the strongest non-material. It also exhibits exceptional thermal conductivity, making it attractive for thermal management. Another property is optical. Despite being only one atom thick, graphene absorbs about 2.3% of incident light per layer. Next one is chemical property. Its high surface area allow easy chemical functionalization, which is useful in the sensor and composite material. Now, this slide summarizes the key application domain of graphene, which arises from its unique combination of electrical, thermal, mechanical, and chemical properties. Graphene is used across electronics, energy sensing, and composites because of its high electrical conductivity, large surface area, mechanical strength, and excellent thermal conductivity. It is especially useful in high frequency electronics, transparent electrodes, sensors, energy storage devices, heat spreaders, and advanced composites. However, due to its zero band gap, graphene is not suitable for conventional digital transistors, and it is mainly used in specialized and hybrid applications. The next type of two-dimensional nanostructure is hexagonal boron nitride or HBN. It is a two-dimensional material structurally similar to graphene with the hexagonal lattice, but it consists of alternating boron nitrogen atom instead of carbon. Although it resembles graphene structurally, its properties are very different. HBN is a wide bandgap insulator of about 6 electron volt, which make it electrically insulating. It is a chemically inert, thermally stable, oxidation resistant, and has a low refractive index, which is why it attracts a lot of attention in nanoelectronics. Single layer of HBN can be stacked to form a few layers of BN nanosheet, and these retain the same excellent properties while also benefiting from high surface area. Because of its atomically smooth surface and electrical insulation, HBN is widely used as substrate dielectric layer in 2D heterostructures, especially with graphene to improve device performance. Now, the another type of two-dimensional nanostructure is transition matter dichalcogenides. Transition matter dichalcogenides or TMDs are an important class of two-dimensional material with a general formula MX2, where M is a transition metal like molybdenum or tungsten and X is a chalcogen such as sulfur or selenium, and they have a layered structure where a metal atom is sandwiched between two chalcogen atoms. Within each layer, atoms are bonded by strong covalent bonds, while adjacent layers are held together by weak van der Waals forces. These weak interlayer interactions allow easy exfoliation into automatically thin layers, making TMDs true two-dimensional material. Structural and electronic properties. In TMDs, the layered XMX structure plays a crucial role in determining their electronic properties. In bulk form, these materials generally shows an indirect band gap. However, when reduced to a single layer, they undergo a transition to a direct band gap. For example, monolayer MOS2 has a direct band gap of around 1 electron volts. This transition leads to strong photoluminescence and makes monolayer TMDs very attractive for photoelectric application. While discussing about unique physical properties, apart from their tunable band gap, TMDs exhibit several unique physical properties. They show strong spin orbital coupling due to the presence of heavy metal atom, which is useful in spintronic application. Monolayer TMDs also display piezoelectric behavior because they lack inversion symmetry, enabling electromechanical coupling at a nanoscale. Now the application of TMDs. Due to these unique properties that are mentioned above, TMDs are widely explored in various applications. They are used in field effect transistor because of their finite band gap, which overcomes a major limitation of graphene. Their strong light matter interaction make them suitable for photodetectors, LEDs, and flexible photoelectronic device. Additionally, their sensitivity to the environment enables their use in the chemical and gas sensing. More broadly, two-dimensional nanomaterials are finding application across multiple fields. They are used in flexible and transparent electronics, energy storage devices such as batteries, supercapacitors, biomedical sensing, and catalytic process. Their high surface to volume ratio and tunable properties make them ideal for next generation nanoscale devices. To summarize, two-dimensional nanomaterial exhibit properties that are fundamentally different from their bulk counterpart. They offer immense potential in electronics, optoelectronics, and energy application. However, challenges such as large-scale synthesis, defect control, and device integration still remain. With the ongoing researches, these materials are expected to play a major role in future nanotechnology-based application. Thank you.